Alrighty. So there's a bunch of talks that are be taking place today about different use cases, different capabilities. So I'm kind of going to talk more as a general concepts and direction and kind of give some ideas for us to think about as the rest of the day goes on. Bill and Oscar have done a great job of kind of leading the charge of saying, sustainability is key. And the idea of this is to give people an idea of why near data compute adds even more value to that concept of sustainability, because it's not just necessarily energy, it's other aspects of what you're doing with the work that we're doing. So as Bill and Oscar mentioned, storing data has a cost associated to it. Processing the data wherever it may land or where it needs to be processed has a cost to it. So energy and cost, sustainability, they're all terms that kind of like what's in a name that Bill and Oscar presented. So it's kind of one of those things, how are we offsetting the cost of, whether it's cost of energy, cost of physical cost, cost of data transfer, and these are all things that we're kind of, what is possible with near data compute as it relates to terms and features of sustainability. So I kind of wanted to focus on kind of four topic areas, if you will. One, as we've talked about very quickly, and you'll hear a bunch about throughout the event, is energy or power requirements. There's an aspect of security that comes into play with some of this aspects of near data compute that people may not really consider, and we'll get a little bit in that. The lifetime of a product. Can we make a given device that was planned for a certain period of time last longer by way of doing things with especially in the case of computational storage, for example, and then end of life and how do we manage that, and it kind of plays back into even some aspects of security. So we can talk about reducing the power consumption by the system, so we're going to move the compute, we're going to offload the compute, we're going to do different things with it, and that helps with the power consumption. And some of it can be offset by you're using a added processing unit that does consume power, but not nearly as much as your general processing unit or your CPU. Other aspects of it can be just using the resources that already coexist in the products that you're building, say, in the case of computational storage and SSD, or in a managed memory device like a CXL device, there's a controller that could have some offload capability that may not be addressed as we would think of it today. And when I talk about kind of security, and I'm thinking through what's going on with the concept of security and near data compute, when we talk about moving the compute closer to the raw data is really the gold that exists in our, oil was the new gold, data is the new gold now. If I have to transmit my raw data from point A to point B to point C, I have security risks that are involved in that. So if I have the ability to take raw data and do transformation of that, which offloads the compute, lowers the power consumption of the overall system, but also now protects that data because it's now not in its raw form, it's in a transformed version of that data. You've now added a layer of security that solves some of those extra hops. We were just talking this before we started, a presentation from a laptop here to a laptop here and how long it takes and all the different hops that data has to transfer across, how many servers, how many security devices, things like that. So by starting to think through security as a way of, if I'm no longer messing with the raw data outside of where I've put it, whether it's in a memory module or it's an SSD, we have the ability to add value to it from that perspective, and it helps with not having to do more security hops through that. I mean, we can all remember what happened with the Cloudflare incident, for example, taking down half the world because all of our data is going through one of their servers because we don't trust our own servers to handle that data. And then reducing data transfers, it's pretty straightforward. We're going to move less data from point A to point B. There's lots of terms that are being defined in the marketplace today, like the number of useful gigabytes per watt or the useful number of bits per watt. So if I have to transfer 16 terabytes of data off of an SSD to sort through it in memory to get 1 terabyte of useful information, I'm spending 15 times more data transfer cost to get access to that data. So near data compute, wherever you're moving from A to B, the transformation of that data helps with that. And this also, from a storage perspective, because I'm a storage guy, so I'm going to play a little bit more on storage, reduces the wear. We can have the capability to not wear out these larger devices because we don't have to constantly rewrite them. As we remember, SSDs today, you write as a page, you read as a block, you erase as a block. If I don't have to erase blocks as often because I'm transforming the data locally and with more efficiency, then I can actually make that product last longer. Therefore, the carbon footprint of that product is also going to reduce its impact and therefore improve your sustainability of a given product. So there's not just one way that we can do this, and there's different paths that we can think through of it. So from a computational storage point of view, you're going to hear a lot about memory and things like that from others as well. And there's a lot of great presentations coming. I kind of put it into what I classify, and you can say it's, blame Scott Shadley for these terms, but bare metal, augmented, and full foreground, if you will, processing. And the idea here is you have ways of doing offload that don't require a lot of significant additional processing power. So compression, we have several folks in the marketplace today that are doing inline compression. And as you can see at the very bottom of the page, there's pros and cons for all of this, and there's opportunities to understand what those challenges can be. You have the encryption, you have the concepts of RAID offload that have been recently introduced. Those are more things that are doing effective work on data to shrink it, change it in a way that doesn't actually transform that data. Compressing is making the data look smaller, but it's not changing what that data represents. Encryption, you're making it harder to read the raw data, but you're not transforming the raw data. Then you get into what I classify as the augmented data background processing, and this is things like I can do CRC checks, I can do other forms of monitoring the data without actually having to transform the data. So I'm going to make sure it matches. I've stored it for a while. Instead of doing these constant read refreshes that you have to do in databases and things like that, pulling all the memory, all the data out into memory, making sure it's the right stuff, and then either rewriting or just saying, okay, that section's good. I can do that on the device. And that gives back processing power to the host. But again, I'm not truly transforming the information that's being stored or moved. And then I call the full foreground, also offload is what I would call it. But the challenge when we talk about these topics, especially over the last 5 years of working through all of this in the industry, is people think when you say the word offload, you're replacing. And there's a very large differential between the term offload and replace. A in-memory compute product, a computational storage product, will never replace our wonderful friends NVIDIA's GPUs or the MIs from AMD, but we can make them more efficient. We can help with the power consumption that they're used. We can help with the usability of those products, reducing the system consumption of energy. I mean, the idea, like, for example, it's always been talked about around, Microsoft is firing up 3 Mile Island. We know why. It's because of power consumption. We're not going to be able to turn off the GPUs, but we can certainly make them much more efficient in the way that they do their work. And so this is things like data prep. You can actually have applications that will do data transformation. So if I'm indexing something or I need to actually change information, I need to relocate what data is representing, I can do full foreground. Representations were one of my former companies where you actually ran a Linux kernel so you could play around with that. So those types of concepts are out there and continue to grow. You'll see here, this is the emerging tech impact radar from our friends at Gartner. They have computational storing as a medium impact, and still a few years out. I'll admit it's taken a little longer than I personally would have liked to have seen happen with this particular technology, but it gives us the opportunity to realize that one of the things about near data compute, computational storage, in-memory compute, these are not a single use item or direction in the industry, and that's been a challenge for a lot of people to kind of grasp, because it's like, well, what's the perfect application? Well, in near data compute and computational storage, there is no one perfect application, right? So if you think about all the different components that are involved in doing this work, it's not simply saying, okay, I'm going to go do X and that's computational storage. I'm going to go do Y and that's in-memory compute. It's a platform or an architecture that's been defined more so than it is a one-stop shop. I mean, if we think of NVMe is our favorite thing for storage today, it's the prerequisite of anything that you put into a system is NVMe. It didn't just come out overnight. It took many years of development, and that is actually a point product. It's a simple transfer interface for an SSD. Yet it took as long or longer than people are saying computational storage is taking too long. Not really, because we're not defining a single solution. We're defining a new way to think about architectures. Our friends at, our friend, Mr. von Neumann, who happens to be a fellow Hungarian, for those that want to know an interesting science fact, defined compute, memory, and storage. 3 succinct elements, and we've lived with that ever since. We've added extra compute, i.e. the GPU next to the CPU. That's fine, but we haven't really change the paradigm of that. And you're starting to see from Oscar and Bill what we're doing in the industry, standard bodies and all that kind of work to do that. We've got presentations coming up in a little bit that are going to talk about very specific applications of these technologies. But I just want, as we move forward with this and we continue talking about computational storage, near data compute, in-memory compute, these are ways of rethinking the architectures that help our developing ecosystem reduce the requirements of assuming there's fixed boxes. We need to start blurring the lines a little more like we're starting to see everybody do. And in the process of doing that, we're going to see energy consumption reduce because we're getting larger drives, which means we have less in the system. We're getting smarter memory because we're starting to do compute in that memory, and we're not moving the data as much because these new architectures are combining elements that we used to think were independent and unrelated from a perspective of this concept of siloing. So we need to break down the silos, lower energy consumption by moving data less, by transforming the data where we find it, not where we think it needs to be. And we're not going to sit here and say that computational storage and near data processing is ever going to remove the need for these succinct elements, but we can certainly make them more efficient working together in that ecosystem. And that's kind of the focus of what I see sustainability. Again, it's not just energy, it's the whole aspects of everything that comes into that. And it's a unique opportunity for us to understand that there's also a lot of the ecosystem we haven't really been paying attention to from a sustainability point of view. So another example is as we start pushing to the edge. And a good example that came out from a good friend of mine who happens to be sitting in the audience is this thing around the hedgehogs in the UK in the zoo. They needed to be able to put up information to be able to watch them and do that. And they created a micro data center in an extra building in the outskirts of the zoo that has now become a place for them to do AI for monitoring habits of animals and things like that in their enclosures. And from a sustainability point of view, the chilling unit they stuck on the side of the building was driving the Chinese, Chinese water deer. Got it right. I had to throw it out there. I saw you in the room. They were in the enclosure next door, and the chiller unit was disturbing them so much they actually had to relocate them to a different spot. So our impact to the environment, our sustainability, our usability of everything. I sat in a session earlier where they were talking about all this energy being released into the air because we're doing this, all the cooling towers and stuff like that. There's environmental impacts to all of that that rely around sustainability. So those are the kinds of topics, things, and directions that from a near data compute point of view we want to kind of pay attention to. It's not just the energy, it's the data transfer, the cost of that data transfer, and then the combination of these architectures. So you do have to realign the data to make certain things work more effectively in memory. You have to think about, are we going to do the traditional RAID striping we've done with hard drives for years and years and years when that's effectively useless in an SSD? Because you don't have to have that worry about the device failing as quickly as they tend to do with the spinning mechanical platters. You have mean time between failures on a hard drive. You have mean time to failure on an SSD, and I'll be happy to debate the two topics there because I was in quality for way too long. So that's just kind of as we think of this moving forward. Again, I didn't want to get into deep diving of a specific example product because we've got so many great examples coming from the other presenters the rest of the day. But again, sustainability, near data compute, and its ability to combine architectural elements that reduce multiple factors in the architecture. That's kind of the focus of that. I know I ended up being a little short, so we're ahead of schedule. So thank you guys for paying attention. Hopefully it was useful information.